I'll begin with a word of prayer. So, Heavenly Father, we again, Lord, thank you for this opportunity we have just to meet together and to study your creation, Lord. I thank you for these students. I just pray that you would give us, focus today to understand what we're doing. I pray, Lord, that you would give the students to ask good questions as they occur to them. And again, then we pray that you be glorified in what we do here this day. In your name I pray, Lord Jesus. Amen. Okay, so I'm going to start by using the projector just a little bit here. I want to show you something called Sage. Sage is a basically free version of Mathematica. It's a little bit more than that. You can operate Sage on the cloud. So whatever that means. Yeah, you don't have to upload it is the main thing. So in your homework, I've asked you to plot a few things. Now, so basically the way this works is pretty simple. You go to sagemath.org, I think. You Google it, you'll find the appropriate link. And once you're there, you can create an account for free and start a Sage worksheet. And then I will cut and paste the code I'm showing you here onto Blackboard. You can cut and paste it on there if you want to do this. If you want to use Blackboard, you're more than welcome. Mathematica. You can do that. If you want to use MATLAB, it's fine with me. I don't care. Whatever.
I just was wondering, do you want to take attendance?
Oh, I couldn't find the attendance, so I'll hopefully tomorrow. Okay. Is everybody here?
Yes. Raise your hand if you're not here. All right.
Okay. Who's not here? Oh. I have two people not here. Okay, so here is I put spin on just to be annoying. You can turn it off if you want, or make it spin slower. Here, if I do spin 5 instead. You have to run the code. It's like a programming language, right? It has to be compiled, much like Mathematica. There's a fair amount you can graph in Wolfram Alpha, but it's not entirely as robust, so I don't encourage that, except in a pinch. But what we're looking right now is the implicit plot of this equation, the level surface x to the fourth plus y cubed plus z cubed equals to 100, which is kind of, I know, it's kind of cool. There's a reason we don't try to classify cubic surfaces or quartic surfaces. There's a lot more of them. I've never actually seen an attempt at a classification of surfaces that are obtained from cubic equations. I don't know if it's known or not even. I mean, that's just my ignorance, but if you change this cube to a 4, it's kind of fun to see what happens. Actually, I'm going to change it to 4th powers all around. What do you think will happen? It's kind of like a sphere, but kind of not, right? So what happens? It's like a dice. What happens if you, let's see here. If I do 6 powers, what do you think that'll look like? More cubish? I think you guys are right. Yeah, it's getting crisper. Of course, if you drop back down to squares, whatever. Here, I want to show you something else while I'm at it. I have a couple of examples. Here, this one's kind of cool. So, I mean, the moral of my lesson here right now is, if you want to visualize level surfaces in general, you really should get some software out and do things, right? That's the best way. There's no guarantee even a simple equation is going to have just one surface that's not disconnected from other parts, right? So apparently cosine x plus cosine y plus cosine z equals to 1 is looks like it's some kind of lattice of spheres. Yeah?
What would happen if you change 1 to cosine to sine?
I don't know. My guess is the spheres will get shifted, but it's going to be the same thing. Same thing. Ooh, kind of the same thing, but it's been shifted. Yeah. Well, these are still spheres. They're just getting cut off by the edge of the universe, which is the cube. So I ask you to visualize some things for your homework. One of the things I asked you to visualize was this thing. You're like, stop doing my homework for me. Well, I still want you guys to actually go do this by yourself. Don't just watch me do it, okay? Care to guess what this is? I have 24 plus x squared plus y squared plus z squared, quantity squared, equals to 100 times x squared plus z squared. An ellipsoid. All right, go and guess for an ellipsoid. I like it. Any other guesses? I give 5 bonus points to whoever guesses it right now. I'll give you 30 seconds. Not 30 seconds, 10 seconds. Guess something. Who? What's that? Who? All right. Now, what? Did somebody say Taurus? You said Taurus. Ah, we have a winner. Those are the easiest 5 bonus points you'll get. Yeah. Isn't that cool? And that come from that equation. Yeah. There are tons of other things you can do. There are tons of other things you can do with this, right? If you look in here, there's other things under plots. Like if I was to go down here, I could plot a parametric surface. You just click on that. It brings down the, there's a preloaded code. And yeah, there's a particular parametric surface. It's kind of snazzy, right? And then, of course, the point here is if you wanted to plot another parametric surface, you could go and tinker with the code and fit it to whatever you were trying to look at. This is all free. It's on the cloud. Use it if you want to. Most everything in this course you can do without this. I don't force the issue, okay? So if we had the class set up so I could have a computer lab once a week or something as part of the actual course, it might be different. But thankfully for you guys, that's not happening here. Hee hee hee. All right, put that away. But this is something else I wanted to visualize with you. So what you're looking at here, this blue arrows, is what I affectionately refer to as rho hat. But before I do this, let me go back just a second here. So this is a ways away. It's a ways ahead in the notes. So here you can visualize x hat, y hat, and z hat. Basically, if this is the x direction, the x hats are the blue arrows, right? There's one of them every point in space. They're just pointing in the unit in the direction of increasing x at one length, right? There's a y hat at every point in space. You can visualize as pointing in the direction of increasing y, right? Z hat, it points in the direction of increasing z with length 1. So I have pictured those, like the green is y hat, the blue is x hat, the red is z hat, and there's a triple of them, frame as it's known, at each point in space, right? It's kind of boring because it's just the same frame, right, moved. Like the x hat, y hat, z hat, what's their formula? Right? And that's the same no matter where you are. So, see if I can do it. Basically, it's, you got this triple, this right-handed triple of vectors, something like this, right? And it doesn't matter where I am, x is always x, so it's just kind of like you move the frame around, it stays the same at different points. So it's kind of even hard to appreciate that it's at different points in space it's being the same, right? Because you just use x hat, z hat, and y hat without kind of thinking about it. They're the same everywhere, they're always just this. But the reason I use this notation, in part, is to set up discussion of the frame of unit vectors for cylindrical and spherical coordinates. So the cylindrical coordinates, you could talk about r hat, you could talk about theta hat, and yes, you can talk about z hat. Well, z hat we already know. That one's boring. But theta hat and r hat are more interesting. R hat turns out to be cosine theta, sine theta 0. Theta hat turns out to be minus sine theta, cosine theta 0. So you can visualize those with a computer algebra system. In this case, I've used Maple to create these pictures. Maple is the competitor for Mathematica. I like Maple, whatever. So here is a picture of r hat. It just points away from the z-axis, right? But if I'm the z-axis, right, then r hat is always like this. If I just kind of turn around, that's r hat. I'm not very good at this. Oh well, sorry. If I had some kind of like glidey shoes, it'd be more awesome, but I should actually get special shoes so I can like just kind of like glide around in a circle. But anyway, the point is r hat just points away from the z-axis, right? But the thing is, r hat points like this way, on one side of the axis. But if you go to the other side of the axis, it's not pointing in the same direction anymore, right? R hat depends on the point. It depends on theta. So it's a variable frame. And theta hat the same. It points in different directions for different theta. But at every point in three-dimensional space, you have a frame. You have a triple of orthogonal vectors that are related by the right-hand rule, the so-called orthonormal frame of right-handed vectors, r hat, theta hat, z hat. Here's a picture of r hat. This is a picture of theta hat. They're wrapping around the z-axis, but they're still in like parallel to the xy plane everywhere you go. Z hat is boring. The corresponding things for spherical vectors, here's the formulas. I don't really want to write them out if you don't mind. Here's the formula for rho hat, for phi hat, for theta hat. Theta hat's the same as I wrote over there. But as you can see, the rho hat and the phi hat, they're kind of complicated. And they also change from point to point. And but they're aptly labeled. They point in the direction of increasing rho, increasing phi, increasing theta. These are things we can use to describe vectors. Here's a picture. The blue ones are the spherical. This is, outward pointing. It's a unit vector in the direction of increasing rho at each point. This is my foolish attempt to draw theta hat. They're wrapping around the z-axis, all right? The ones that I think are harder to picture is the phi hat. That's the red. Those, so as you, well, here, I'll just draw a single picture. If I pick this point, then phi hat would point down like this. It points in the direction of increasing phi. Rho hat would point like that. And depending on how you understand things, I mean, it kind of depends where this is. If it's directly in the YZ plane, if that point I'm drawing is in the YZ plane, then theta hat points directly into the board, which I could illustrate by using this symbol, cross like that. So there's theta hat. Theta hat points into the board. You can think of that as being the tail fins of the arrow pointing, like the arrow's pointing into the board, so you're seeing the tail fins of the arrow with that picture. Here is something I would not try to draw by hand, but here's a picture of the phi hat, the theta hat, and the rho hat all at once, I think. So the rho hats are the blue arrows, the phi hats are the red arrows, the green arrows are the theta hats. At every point, you have this triple of unit vectors that you can build other vectors from. So this is why I use the x, y, z notation, x hat, y hat, z hat, is so that it's a natural departure to talk about rho hat, theta hat, phi hat. You're like, well, why are you talking about these at all? Because I don't have enough sense to not to. I don't know, mostly. Listen, this is just another language we can use to describe vectors. I've given you a sample homework problem on these. We will come back and use this language from time to time as it's convenient to us. These notations are very common in engineering and in physics, and that's why I go over them. Nope. All right, well, with that, I have gotten basically the algebra portion of this course out of my system. I have pretty much no more just plain algebra to show you. We have covered the necessary bits and pieces. And that brings us to the problem of calculus, right? So in this course, we'll cover the calculus of many variables. And so you could have many variables in the domain of your function, and you could have many variables in the range of your function. We start by looking at the problem of having many variables in the range, which is the easier thing. Oh, I wanted to get rid of that, sorry. So basically, we're going to be looking at how you can do calculus with the formulas we understood to be parametrizations of curves. All right? So just to give you kind of a view ahead, today, calculus for curves. And so what we're really talking about is mappings of the form t maps to something like r of t. So we're talking about how to differentiate and integrate such things, okay? Later, we'll talk about the calculus for things like z equals to f of xy, functions of several variables. That's where we talk about partial derivatives and so forth. Later still, we study the combination, right? Like something like x of u v. That would be like a parametrization of a surface, was that kind of thing. We study the calculus of those later. Okay? So for today, we're studying the calculus of curves. So let me give you a definition. Now, I could give you a definition in terms of limits, but I think you'd be happier if I gave you a definition without limits. Am I right? Yeah, I thought so. So if, let's say, r is equal to x1, x2, xn, right, where x1 through xn, these are functions of t, all right? So in other words, what we have is that x of j is a mapping from the domain of R, which is some subset of the reals, to the reals again. Each one of these is a real valued function of a real variable. Okay. Given that setup, all right, dr dt, which will also sometimes denote r prime of t, all right, it's simply the following. It is dx1 dt, dx2 dt, all the way out to dxn dt. In other words, to differentiate a vector-valued function of a real variable, we simply differentiate component-wise. The first component, then the second component, all the way out to the nth component. Simple as that. I'm kind of greedy. I'm going to give you the definition of the integral while we're at it. The integral of r of t dt. I'm talking about the integral of a vector of functions, really. It's simply defined to be the vector of the integrals. And I'm starting by giving you the indefinite integral. Right? But, so, you guys with me on that? That's an indefinite integral, which technically means that you're not getting a single function as your answer, you're getting a whole family of functions, which are related by, as it turns out here, a constant vector shift. We had a different constant in each component. There's no reason the constants for the different components would be related. That said, the definite integral is likewise defined. If I go from t1 to t2, I just put the same bounds everywhere. Okay, that's the definite integral. Just like that. Shall we do an example? Is there a question?
What is a function
Function. Oh, r, yeah. I think I was writing r and then my brain skipped. This will happen. Other questions? So an example. Now, I gave you the definition for n dimensions, but most often we'll either be working with 2 or 3 dimensions, right? In which case, geometrically, you can think of what we're looking at as the parametrization of either a curve in the plane or it's the parametrization of a space curve, a curve in 3 dimensions, right? Let's see here. How about this? R of t equals to e to the t and t squared. So what's dr dt? I'm going to write this step out this once. This may be the last time you see me write this step, okay? Enjoy it. All right? You're like, well, I'm glad you're not going to keep writing that step because I don't want to write that step either. And so I'm happy that you're not writing that step because that means you're not going to take off points when I don't write that step. That's true. Generically speaking, whatever I do, it's usually okay for you to do that. Now, if I don't do that, you may be in danger. I don't know. But there it is. How about integral? So we do the integral of e to the t dt, the integral of t squared dt. What's that? E to the t plus c1. I'm glad I all heard you say c1. Thank you for that. Was 1/3 t cubed. But I'm sure you all have felt the pain of not adding the constant and losing the token 2 points and going, ah! I could have lost those points in a better way, right? We've all been there. But yeah, we have to add constants for the indefinite integral. But I would point out to you that we can rewrite this as what? Plus c, where c is a vector of unknown constants. And I mean, c is, what is this c, you know? Es bueno? Muy bueno. Very good. 2 to the t times the hyperbolic cosine of t, and the sine of the square root of t. How would we differentiate this thing? Did you zoom in, by the way? Because if it's zoomed out like I had it, it won't be good. Okay, cool. So let's differentiate. Let's calculate. dr dt is what? Let me not use this marker. It doesn't show up very good. What's the derivative of 2 to the t?
2 to the t minus 2 divided by minus 2.
Is the natural log of 2 times 2 to the t. How about the next thing? What's the derivative of t times hyperbolic cosine of t? Yep. Now, why are there 2 terms? Because of the product rule, right? Or the Leibniz rule. You're like, this is calculus 3. Don't insult me by telling me there's a product rule. There's a precedent for this. Your predecessors, I gave a first quiz, and without thinking about it, I put something like t times sine t as one of the z components, and then I had the class differentiate, and most of them put, like, I forget what they put down, but usually just 1 times cosine t. I don't know, like 30-40% of my class no longer knew the product rule. I guess I could blame the summer or something, but I know you guys forget if you don't use it. So, was there a question? Yep. Oh no. Here, let's work it out. So if y is equal to 2 to the t, and we're uncertain, as apparently we are, then I can convert this by taking the natural log of both sides. That gives me natural log of y is natural log of 2 to the t. But everybody knows that that's t times the natural log of 2. Then I differentiate implicitly both sides. This gives me 1 over y dy dt is equal to natural log of 2. And then that gives me that dy dt is y times the natural log of 2. But you can recognize, as my daughter says, that that is derivative of 2 to the t times natural log of 2 times 2 to the t. You're thinking of integration. If we forget how to differentiate in, certain things, we can use logarithmic differentiation to connect to integrals that we know. I mean, derivatives that we know. Okay, how about the last one? What we got? We got cosine of the square root of t times the derivative of the inside function, right? This is chain rule. So I've got 1 over 2 times the square root of t. And there you have it. Don't worry, I'm not going to try to integrate this one. I think you'll find the integral of the sine of the square root is kind of hard. T cosh t I can do. That's integration by parts, but whatever. Okay. How about some interpretation? Just stop and smell the roses here for a second. If r of t is the position of a physical particle, what does dr dt represent?
Velocity.
Yeah, it's the velocity. It's the velocity, which is a vector, right? What would r prime prime of t be? Here, I'm a glutton for punishment. Let's calculate the acceleration here. R prime prime of t is what? Which, by the way, we could also denote as d squared r dt squared, right? Different notations for the same animal. First piece is easy enough. That's natural log of 2 quantity squared, 2 to the t. Then I get sinh t, plus sinh t, plus t cosh t, comma, minus the sine of the square root of t divided by 2 square root of t, quantity squared, plus cosine of the square root of t divided by 2. And then I have to differentiate 1 over the square root of t. 1 over the square root of t is what? 1 over the square root of t is t to the minus 1/2, right? So if I differentiate this thing, I've got minus 1/2 t to the minus 3/2. Of course, you can clean this up. The point is, if you got a product, you got to do the product rule. And if you got an inside function, you got to do the chain rule. If you don't know how to do product rule and chain rule, if you don't know derivatives of hyperbolic sine, hyperbolic cosine, sine, 2 to the t, stuff like that, you probably should review it. Okay. Yeah, of course, this can be simplified. It's 2 sinh t's. I just was leaving the terms as they occur to me by applying product rules. So. He's good? Well, anyway. Let's see here. I'll do another example, but first I want to introduce a new concept, tangent line. To space curve. So the space curve is t maps to r of t. So basically the picture is something like this. I don't know. Here's your x, y, z. And I want to describe how to parametrize the tangent line to the space curve at a particular point. I'll pick this point for the purposes of my artistry. So basically my base point of tangency, is going to be r of t naught. So what's the direction vector of the tangent line? Well, you could use a unit vector, I suppose, but I'm going to be more free form about it. So here's the tangent line. Right? It's a line in 3 dimensions, so the best way to describe that, as we've seen, is parametrically, right? So let's say L of t is the tangent line. So what I would do is r of t naught plus what? That gives me the base point. Yeah, so the direction vector would be r prime of t naught. Or if you will, the velocity vector, right? Now here I'm assuming that the curve is parametrized curve, right? So it's got a direction, it's oriented. And I'm supposing that the flow of the curve is as I indicate, like that. So the velocity vector points you in the direction in which the curve is going, at least infinitesimally. And the tangent line is the best linear approximation to the curve, really close to the point of tangency, right? Of course, it doesn't have to look anything like the curve as you get further away. That's supposed to be a line. It looks more like a curve to me. This is supposed to be a line. Use your imagination. So what's the formula? R prime of t naught. And then you can just multiply by t. I could put the t before or after. I'm going to put it before just so. Now, if you don't like that does make the t of the tangent line different than the t of the curve. If you want it to match up, if you want to have the time match up, how would you do it? You could use this formula. You could use r of t naught plus parentheses t minus t naught, r prime of t naught. If you use that, let's call that, I'm going to call that LT naught just to give it a stupid name. If I do that, then LT naught of T naught is equal to R of T naught. The parameters match up if I do that. But if nobody forces you to do that, you could just put T there. It's also a perfectly good parameterization. That just puts T equals 0 at the point of tangency, as opposed to putting the point of tangency at T equals to T naught for your line. I'm not sure how good a job I did of drawing the twisted cubic the other day, but the kind of awesome thing about calculus of space curves is I can easily find you a precise and unflinchingly correct description of the tangent line to the twisted cubic at a point, even though I'm powerless to graph it accurately as a human. Well, a human with a computer, I could graph it pretty well. But again, forget about those computers for a second here. So how about this? R of t, t squared, t cubed. This is the twisted cubic, which is kind of a nasty, well, it's not too nasty. And what I want to do is find tangent line at 1, 1, 1. Okay? Oh, I forgot to, the point of this monstrosity is that's the acceleration. It's the acceleration of this, if this is the position of something. So you multiply that by mass, that gives you the net force which is on that thing. Ugh. Yeah, okay. There it is. Okay, so how do we find the tangent line? very simple. I calculate r prime of t, which is what? 1, 2t, 3t squared. Remember, to actually find the tangent line, I have to plug in the parameter that is of interest. In this case, which one is that? T equals to what? I didn't tell you what the parameter was. How do you figure out the parameter? I mean, there's not much to figure out here if you're... But in principle, I set this equal to t squared t cubed, and I solve it. If I can't solve those three equations simultaneously, then you've been sold a bill of goods. You've been asked to find a point which isn't actually on the curve. Of course, this one is, and the parameter is 1, right? So r prime of 1 is what? 1, 2, 3. And so the tangent line I'm looking for, L of t, I can just use 1, 1, 1 plus t times 1, 2, 3. And that, folks, is the tangent line to the curve at that point. So if I was so foolish as to draw this thing, I won't really try. I don't know, it's something like that, right? And then this point maybe is 1, 1, 1. We found the equation, whoa, for the tangent line, L. Any questions? Would you like me to do another one of these, maybe? Yeah, I'm going to do it. That means that I plug in time equals to 1 into the velocity, into the r prime, to select the direction vector. That's the significance. If I'm going to find the tangent line at that point, I need to figure out what parameter corresponds to that point. In this case, t equals to 1. Yeah. In my next example, it will be slightly more exciting. So look at r of t equals to cosine t, t, sine t. And let's find the tangent line at, oh goodness gracious, 1. Not helpful. 4 pi. Oh, see, this is no fun. These are still, it's still too easy. Oh man. The reason this is too easy is because when you set this equal to the curve, right? When you set this equal to curve, so this is the problem statement, all right? So when you set this equal to the curve, it's immediately obvious what the parameter is. What? It's not 1, no. The point is when t is one of the parametric functions, you can just compare this and this and go, oh, t is 4 pi. So it's kind of like a non-event, yeah.
All right. This is sort of on the right board. You need to put for your equation r of t naught plus t minus t naught, r of t naught.
Oh, this is supposed to be r prime of t naught, of course.
Okay. Just want to make sure.
Yes. So what's dr dt here? It's minus sine t, 1 cosine t. What that means, by the way, is that this curve is climbing it's going in the y direction at the same rate at different points, right? I mean, this is actually a helix that is climbing the y-axis, so that makes sense. But anyway, so there's the velocity, then r prime of 4 pi. is minus the sine of 4 pi, which we should know without picking up a calculator, right? You guys should know sines and cosines of multiples of pi without seeking technological help. What's sine of 4 pi? 0. What's cosine of 4 pi? 1, right. Very good. 0, 1, 1 then. And so the tangent line is, I'll do it this 1, 4 pi, 0, and I'll sync it up this time, plus t minus 4 pi times 0, 1, 1. There you go. You could, you can either make it sync up, or as I did in the last example, I just put t equals to 0 as the point of tangency. This formula puts t equals to 4 pi as the tangent point, even for the tangent line parametrization. There are probably some instructors who insist that this is the only way to do it, and what I did over here is wrong. But I don't have too much respect for them, obviously. Anyway, I've also not met them, so I'm just talking about a hypothetical person who's out there somewhere. Maybe they'll leave a nasty comment on this video. I don't know. I shouldn't encourage that. Okay. Any questions about these? Do you think if I gave you a space curve and asked you to find the tangent line, you can do it? You're like, as long as I can do the derivatives, right? Yeah. I hear you. What are the properties? What are the properties of these derivatives that we're talking about, right?
Why did you do t minus 4 on the quantity of the vector 0, 1, 1, and not do t minus 1?
Choice? Just a choice. I didn't specify otherwise. If I had added the instructions, force the parameter of the tangent line to match r of t, then this would be the necessary answer. But in lieu of those instructions, you could either go this way or go that way, is my point. Because either one of these is a parametrization of the tangent line. Yes, indeed. Or I could even do something like t minus 10. Frankly, I could replace this with something more awful. It would still trace out the same point set, right? So this is an ambiguity that's always there with parametrized curves.
You could have put 3000 t or whatever else you wanted in that slot.
Yes.
As long as it had the whole.
But I suppose the nice thing about this tangent line, using t or t shifted, at least the velocity of the tangent line matches the velocity of the curve, and that's kind of a natural thing to have. What are the properties of these derivatives? Well, since we only have 3 minutes, I say we'll talk about them tomorrow, okay? Am I right? Right, we only have like 3 minutes left, right? Yeah, so you can cut it off.